So let me start with the motivation. It's just as the description on the Simmons collaboration on celestial holography. I guess most of the audience are interested in applying the idea to flat space-time, like the one we inhabit. So in this talk, my goal is precisely the same, and the tool I'm going to use is the top-down approach. So as we all know, AdS₃ has been first constructed in string theory. So today I'm going to start from an explicit model of AdS₃ constructed from string theory. And then I would like to deform this duality from both sides. And on the string theory side, I'm going to do this TsT deformation, and on the field theory side, it's something related to this so-called single trace TTbar deformation. So in the end of the day, we try to get a toy model of holography for asymptotically flat spacetime. So let me move on. So the structure of this talk can be described by this two-layered triangle. The inner layer is the theory of duality we start with before any deformation. So this is a model of AdS₃ CFT correspondence constructed in string theory. And if we consider the theory supported by NS fluxes, it allows a third description. It's the string worship description, and this three-dimensional part is the SL2 WZW model. So in the following, I will first describe the inner triangle, and then start deforming the theory, the three corners, and I will introduce what we are doing at the three outer corners, and then finally I'll mention what has been matched in this outer triangle. So this talk is based on a serious work with my collaborators, including Louis Apollo, Wei Song, Stephen Dieterle, and Zhengyuan Du, who is in the audience, Wenxin Lai, Kangning Liu, Shu Hongfei, Juntao Wang, and Boyang Yu. Lots of them are my current and previous students and postdocs. Okay, let me start with the inner triangle. So I start with Type IIB string theory, AdS₃ with 7-dimensional internal manifold supported with NS flux. So here is this AdS metric, and for instance, we can write this Pangari AdS. Gamma and gamma bar are two null coordinates, and phi is a radial coordinate, and this capital Phi is the dilaton. It has the solution has a non-trivial B field, and the electric charge and magnetic charge correspond to this. If we take this from this NS1, NS5 brane construction, they correspond to the number of D5 branes and NS1 branes. So this model can also be related to this famous D1, D5 system by S-duality. So that's the basic setup in Type IIB supergravity. So because this is NS background, so the worldsheet theory can be written down and studied, and the AdS₃ part is this SL2 with Zumino-Witten model, and so here is the theory. Lots of people are familiar with it. What I want to stress is that the perturbative spectrum of this theory contains two parts. One is the so-called short string sector, and they are characterized by this representation, discrete representation of SL2, and also a spectral flow parameter W. And there's another sector, this long string sector. These are continuous spectrum and also characterized by this Casimir G and also this winding number W. So for the continuous representation, it is very important that we have to include this winding number. So to understand this winding, so there is a classical description. So basically, starting from states without winding, at the classical level, you can just change the solution by adding some zero mode to the classical string solution to the the time direction and phi direction in global AdS spacetime. And more concretely, the algebra will have a spectral flow, and the states will have a shift in the eigenvalue of this J3, the zero mode of this J3, where J3 is the translational generator of this global AdS now translation. So it also changes the Virasoro zero mode, actually affect also other generators in the worldsheet Virasoro. So we know the physical states have to satisfy the Virasoro constraint. Because of this non-trivial winding, this Virasoro constraint will get an additional contribution due to the winding. So we'll go back to this fact later. So that's basically the bulk theory. We have a supergravity description, which allows the classical solution. We also have the worldsheet description. And now come to the most tricky part. So we know from our experience there must be a CFT dual to this theory. But what precisely is this CFT? There are lots of discussions and debates. The clean result is at the k equals to 1, where this short strings, they just disappear, and the long strings, this continuous description, they just truncated to the only allowed value of j that equals to a half. And there, the holographic dual has been argued to be the symmetric product. For generic K, the long string sector, nevertheless, can still be, for lots of questions, can be characterized by a symmetric product structure. But of course, if we want to understand the full theory, we also need to add some marginal deformations. So in this talk, I will focus mainly on the long string sector in the gravity set, in the string set, and focus on the symmetric product part of the CFT part. So there is a there is a map between the bulk and the boundary. For instance, these null directions are mapped to null coordinate in the CFT, and another current that generates null translation on the space-time will correspond to the stress tensor. And since we have a symmetric product, the stress tensor is the sum of the stress tensor in each copy of the state CFT. And then, well, I know you're going to ask. So I'm most nervous about this question. I will talk about, I will focus on the long string sector at generic K because I'm just doing the bosonic part. But the most precise agreement or precise duality should really be done in the case at k equals to 1, where you need to really look at the details of the series on both sides.
Yeah, the reason I'm asking is that you pronounce the word symmetric product, but I guess it's for k greater than 1, so what exactly do you mean by that?
It's the symmetric product of this linear dilaton times T4.
And you're assuming it, some pieces of it survive after you turn on these marginal deformations that you need to turn on?
Well, that's okay. What I can say is that we will do some kind of calculation, assuming that there is a symmetric product, and we say that lots of quantities can be matched. I would expect there is a version of single trace TTbar after you turn on this marginal deformation, but I don't know how to do that. And
we can probably discuss later. I have said single trace TTbar is defined to be the symmetric product orbifold of TTbar. So if you don't have an exact symmetric product of full structure, but maybe we should leave this.
Yeah.
What's capital N?
Capital N is the number of is the electric charge. It's in terms of the symmetric product, it's the copies of your seed theory.
I have a slight question. So here, you just said you all basically talk about long string sector. But what do we know anything about the short string sector and what's the dual?
It's a mystery.
Oh.
Even before any deformation, it's very complicated. We know something about the Carroll primaries, but in general, I don't have much to say about it. Okay, so let's go back to long string sector, and this winding in the bulk is mapped to this. In the symmetric product, the spectrum is characterized by different twisted sectors, and this N, I use this little n to label the twist in the symmetric orbifold. So W for the long string is mapped to N in the twisted sector. In particular, when W equals to 1 in the bulk correspond to the untwisted sector. And so if we consider this spectrum and then consider this SL2, and it's the eigenvalue of the G3 that is roughly matched to the space-time conformal weight in the dual field theory. So that's the starting point. There are already tons of issues here. What I want to say is that before the deformation, there is a duality or a triangle there. It exists. There are still some issues about what the dual CFT is precisely is. But some features of the CFT can still be captured by a symmetric product. So let me move on to do deformations. So in the bulk, I'd like to do this so-called TsT transformation. Suppose we have, say, a super gravity solution with two global UN symmetries. We have two explicit asymmetry directions in the bulk. Let's call it broadly. Let's call them two UN directions. We can do this T-duality along one of this UN, and then shift the other U1. Sorry. Shift the other U1. This Mn is the first U1. We do T-duality along this, and then shift the other one by the first one. And the coefficient here, I call it this, parameterize it by lambda. And then I do T-duality along the first one again. If we don't mix, we don't shift in the middle, we go back to the original theory, nothing changed. But this shift is really non-trivial. It leads out to a completely new solution. In particular, we can do this to this, say, the AdS₃. Then after that, we'll get a completely new background. It changes the asymptotically completely. So as we can see from the solution, I colored this lambda here. When it is 0, it goes back to our original AdS. But as long as this is non-zero, we can see as the radial direction phi goes to infinity, the metric is really flat. But at the same time, we can look at the dilaton. So as this radial phi goes to infinity, we see that this dilaton phi is proportional to this minus phi, which is the radial direction. So we can calculate, of course, you can see the string free metric looks like flat, and you can really calculate the curvatures. And both the string frame curvature and Einstein frame curvature, they goes to 0. So in this sense, we will say this is a background that's asymptotically flat. Yeah.
Maybe Monica's lecture notes and Herman's from before. To what extent this T-duality shifting in T-duality is now standard, or I mean, I thought before there was a picture where I do a TTbar deformation, I'm just literally moving some screen closer and closer to the bulk of AdS, or when you're talking about reproducing different asymptotics, what's the I don't know, could you make any statement about the extent to which this TsT TTbar correspondence is the only thing you can do, and it's a more informed version of previous literature or not?
I'll comment on that maybe later.
Yeah. It's the difference between single trace and double trace.
Okay.
Double trace doesn't change the asymptotics, which is the one you talk.
Can you speak up or use microphone?
Maybe I'll comment on that later. Yeah. Okay. We can also apply the TsT transformation to all these BTC solutions, and we will generate a bunch of black hole solutions. Yes.
Sorry, can you comment on the asymptotic structure on the Penrose diagram of this spacetime, and what's the difference with flat space?
The Penrose diagram, yeah.
Similarities and differences here.
Okay. So in what I'm going to do, we are putting the dual essentially on a time-lag boundary, where this Euro celestial holography is at the null boundary. I hope there in the end there will be some connection between these two, yeah, because I'm literally taking this phi to infinity. So, okay. Okay, that's basically the bulk. Okay.
Is the scalar coverage 0 for p-value of lambda or only for non-zero lambda?
The scalar curvature goes to 0 when phi goes at infinity for any lambda.
Oh, it's not 0 to 0 and.
No, it's not. In the bulk, it starts with, so you see, this rho is phi, rho is phi. So when the radius is very small, you can just forget about this lambda term. This is nothing, it's AdS₃. So the curvature starts from like negative and then gradually, if lambda is positive, then it gradually becomes 0. When lambda is negative, I have a diagram later. So there is something interesting in the middle. Okay. Okay. Let me start talking about the deformation in the field theory side. I mentioned TTbar, so I need to start with the standard TTbar. So it's familiar to lots of you. So the standard TTbar can be defined as from this differential equation of this deformed action at any deformation parameter mu, and its derivative with respect to mu is basically the determinant of the stress tensor at the value mu. So this theory is solvable in the sense that if we pose theory in the cylinder, the spectrum of the deformed theory is related to the undeformed theory in a known way. And the formula is very simple. And it has lots of other interesting properties that I will not just mention. So let's just focus on the spectrum. So the spectrum actually, the property depends on the sum of this deformation parameter. So if we consider this negative sum, so we'll see something like if we start with the states at 0 deformation and then start deform it, we'll see the states at lower level, it's more dense and become more sparse at higher level. And meantime, there is a value of the high energy where the what's inside this square root starts to become negative, and there seems to be a cutoff of this energy. And what about the other sum? Before that, that's related to your question. So before this standard defined TTbar deformation, there's this holographic proposal. So if you start from AdS₃ correspondence and you deform CFT by the standard TTbar deformation, the proposed holographic duality is that one proposal by Herman and friends is that you put a finite cutoff in the bulk. And also there is the alternative understanding that is to impose mixed boundary conditions and in this holographic renormalization point of view. And for pure Einstein gravity, the 2 point of view are actually the same. And now, how about the positive mu? There's no issue, at least the high energy states, they won't become complex, but they become denser and denser. Actually, they have a hexagon growth, and that's there is upper bound of this temperature. That's the hexagon temperature determined by this 1 over the deformation parameter. And there's some worrisome property at low energy, actually just the ground state, because we know the ground state of a CFT is negative. If mu is positive but large, then this ground state may become complex. So then there is a critical value of this deformation parameter. In some units, it cannot be larger than a half. So there is a critical value of this deformation parameter. So if we want a theory to be unitary and good for all states, we probably want to work with the positive parameter of this combined lambda between 0 and a half. Yeah.
So can I reinterpret that to just try to understand? Like, if I did the very nice thing of trying to interpret that cutoff and then bring that cutoff all the way into like a sub-AdS scale, there's something sick about doing that in the old story for trying to get a flat.
Yeah, in the old story of Herman is that the high energy problem is that if you can put black holes in the box, but the black hole horizon cannot be larger than the box scale. So then the cutoff for the energy is when the horizon coincides with the cutoff. And then there's, of course, this. You can also ask about the holographic dual. Actually, the mixed boundary condition proposal also works with this sun. Alternatively, we can also glue another patch of AdS to the asymptotic boundary of the original one. It's like analytic continuation of the cutoff picture, and some properties of that also work. But I won't talk about that. So this is the story of the standard TTbar, but we are not going to use the standard TTbar. We are going to use the so-called.
A naive question. So before you do the mu deformation, you also have a hydrogen growth, right?
In standard.
Yeah. Do you have that? Or does hydrogen growth is the result of deformation?
It's the result of deformation.
Oh, okay.
I thought it was string theory before, right? Before the deformation, so why don't you?
Okay, since you let me go back. So I can also mention a few properties of this double trace TTbar. So from this diagram, we can see that after deformation, the states they don't cross. So you can see, okay, the number of the states they don't change. So if we start from the Cardi region of the CFT, we have the Cardi formula to count the number of states, and then we have a precise relation between the deformed and undeformed energies. We can just write the Cardi formula in terms of the deformed energy, and we get this formula. This is the entropy formula for the TTbar-deformed CFT. This formula can alternatively be derived by using an argument very similar to what Tom and friend did for CFT. If we consider the starting point before the deformation, if we consider a large C CFT, and if we assume this sparseness condition for the lattice states, then what we'll get is that the torus partition function can be approximated for both the lower temperature and also the high temperature. And the approximation is basically at the low temperature, it's essentially the contribution from the vacuum state, and then the high temperature is the modular S-dual of that formula. So if we forget about the earlier argument about the entropy, start from modular invariance and get the partition function, we can also derive the same formula.
Sorry, I have a naive question. So what's the C here? It's a 6N?
C
C is the central charge, right?
C is the central charge before, we assume we TTbar-deformed a CFT. C is the central charge of the CFT.
Yeah, the argument requires large C.
Yeah, large C, yeah.
Here your C is N. It's a large number?
Oh, you want to go ahead? Yeah, yes, yeah, it's N, yeah.
Oh, okay.
It's 6kN.
Yeah, okay, yeah.
Okay. Okay, now I go to single trace TTbar. So far, single trace TTbar is only defined to symmetric product CFTs. So the story is that instead of making the symmetric orbifold using a CFT, you use the seed you choose is the TTbar-deformed CFT. So you first do TTbar, ordinary TTbar to a seed CFT, and then you make this symmetric orbifold. You'll get a new theory. And this new theory, surprisingly, you can still assume modular invariance. And if you assume modular invariance, what you can see is that it's very similar to the old story of symmetric orbifold. It requires twisted sector. And the energy of the twisted sector is related to the untwisted sector in a particular way. And that way, we can just derive this single trace TTbar energy in arbitrary twisted sector. And in the untwisted sector, it agrees with the double trace TTbar. And the modification to the single trace TTbar entropy formula is that you see it has an N there, where N is the copy of your symmetric orbifold. Okay. So now I've described the basic ingredients I'm going to use. Now it's come to this the statement. What I mean by TsT, TTbar correspondence, is it's just a name. What it refers to is that if we start from type IIB string theory, AdS₃, with NS flux, we start with this inner triangle. We do TsT transformation in the gravity side. And we found quite interestingly, there is, if we do this single trace TTbar deformation in the field theory set to symmetric product theory, there are lots of quantities that can be matched to each other. You may immediately argue to me that this field theory is not really a symmetric product, but I admit this is true. What I expect is that this at the moment single trace TTbar is only defined to symmetric product series. I expect that there is some version of single trace TTbar that can be defined after you add this marginal deformation to the symmetric orbifold that really due to the N-deformed theory. Or alternatively, the discussion I provide later today can still survive this marginal deformation. I don't know how it works. I can only describe what I get from this symmetric orbifold construction and what can be matched.
Is it obvious why the TsT corresponds to a single trace and not the other one?
Well, a very intuitive argument is that this TsT really changed the asymptotics. And double trace deformation will not change the asymptotic. It will not change the geometry. Yeah. So if we really wish something that can correspond to the TsT, it has to be something that has some feature of single trace. Okay, so I also want to mention that this observation of the background that I gave you, this linear dilaton background and this single trace TTbar deformation was first proposed by Kudasov and friends. But their proposal and what I'm describing now, there are some lots of similarities, but also some differences. One thing is that there in their proposal, there is no additional parameter lambda. So their deformation parameter is basically the string length. Where here we have an additional parameter. It's completely independent. And also the observation that this TsT transformation, as I mentioned, it can be done to arbitrary U1 directions. And if you do this TsT to different directions, you will get different bulk geometry. And in the boundary, they will correspond to different solvable deformations. For instance, if we do TsT transformation to the two null directions in AdS₃, we get this linear dilaton background. And the proposal is that it's related to single trace TTbar deformation. Alternatively, if we choose to do TsT along one null direction in AdS₃ and another direction in, say, S3 or T4, then we will get, in the bulk is three-dimensional part, we will get the so-called warped AdS spacetime. And this is closely related to Kerr CFT. Yeah.
AdS₃ system just for one value of this TsT parameter, or you're going to be getting it for any value, you just have to rescale stuff?
It's any value of what?
Of the TsT parameter.
It's arbitrary. It's completely free.
Okay, but do you have a match? So you can also get this linear dilaton geometry from the decoupling limit of the AdS₃ system. Do these two things coincide? When do they coincide?
That corresponds to a particular choice of R lambda. In some parameterization, it's like lambda goes to a half or something.
And the other choices correspond to?
It's detailed matching of their solution and ours. There's one way of parameterize the solution. If I remember correctly, their proposal corresponds to a particular choice of this lambda here. Yes, they are completely independent. No, TTbar-like thing has a mu. And mu is mu. Yeah, it's yeah.
Sorry,
No, no.
I have a naive question. So here in the previous slide said that the original proposal for generic safety, but you said this single trace TTbar only applies to the
Symmetric part.
safety.
Yeah.
Why it does not exist for the non-symmetric safety?
Well, it's at the moment, the definition of the single trace depends on the symmetric product structure. So,
Maybe you have not read down the definition of the single trace TTbar.
well, my expectation is that there is some version of that for generic safety, but I don't know how to write it down or how it works. Yeah.
Does your linear dilaton background have a scribe?
In order to do so, I need to scale my radial direction and the null direction in a very particular way, which I'm not going to. We haven't looked at that particular limit. Yeah.
You think such a thing could be done? And could you define a scattering amplitude if you did that?
Well, one thing, this is 3D first, and I don't know. I haven't done that. Yeah. Okay, and also you can do a linear combination of, so this toy model for curl CFT is that the boundary is the single trace version of TTbar deformation that Monica initially proposed. And then we can do a linear combination of lots of things, TTbar, JTbar, TJbar, and we can show that for all of this, you can obtain them, the bulk, by several TsT transformations and lots of structure still matches. Okay, let me briefly give some intuition why it should work. So if we do a TsT on the worksheet, you can show that the worksheet action satisfies a very beautiful formula. The derivative with respect to this lambda, the TsT parameter, can be written as this current of these two U1s that you do TsT with, and these currents are the instantaneous current of at a parameter lambda, and that may ring a bell because we know for TTbar and JTbar deformation, they can also be written in such a way. This deformed action satisfies a differential equation where the right-hand side can be written as the current product. And you can just follow the symmetries. So in the bulk, if we do a T along the null direction and the T bar along this another null direction, and the currents, these currents are the worksheet Noether currents of these two null directions. And if you remember the dictionary I mentioned at the very beginning in the inner triangle, the two null directions in the bulk is mapped to null directions in the CFT. And in the CFT, what are the currents that generate these null translations? They are just the stress tensors. And then in that case, TTbar is, you can write, of course, this Noether currents as one form, and that's precisely the TTbar deformation. So it's the worksheet, the TsT, and the TTbar, and also other irrelevant deformation can all be written as this differential equation that they satisfy. The right-hand side is just the, this current deformation. Okay, then about the spectrum. So as I mentioned, on the string theory, it is a TsT transformation. And we have introduced this spectral flow parameter, the W, which is also the winding. And so the TsT transformation, as shown by Ode and friends on the worksheet, can be related to a non-local coordinate transformation. Okay, I need to hurry up a bit. With non-local field redefinition, so that the worksheet equation of motion after the TsT is equivalent to the worksheet equation of motion before the deformation, namely the WZW model equation of motions. But this field redefinition will mess up with the boundary conditions. So the variables before and after the deformation, if we choose the variables after the deformation to be periodic on the string worksheet, it will introduce this non-trivial winding in this AdS coordinates. But as we know, this introducing a non-trivial winding can be treated as a spectral flow. So this TsT can similarly be treated as a spectral flow as well. But this time, this twisted boundary condition, the twist parameter, depend on the momentum. So this you get a momentum-dependent spectral flow. But nevertheless, if we look at the classical string solutions, you can find all the solutions of the TsT transformed string theory and find the relation between and after the deformation. So there's there's more details about what's going on here. So if you start with certain periodic solutions, you plug it into the Versor constraint, and if you introduce ordinary winding, it will lead to an additional term. W times R is its radius, and P is the momentum of the spectral flow direction that you are introducing. And this is the ordinary spectral flow along certain U1 direction. And this TsT operation can also, where this non-local coordinate transformation can also be interpreted as a spectral flow transformation, and that will introduce another term. And the spectral flow parameter, this W, will depend on a momentum. So that's why it introduces a term like lambda PP bar here. And finally, if we combine these two effects together, we have ordinary winding, and also we have TsT. Then we can compare the spectrum. We need the Versor constraint to be satisfied before and after, and we decide to trace a certain operator or certain state with the same internal excitations and also the same representation. And what we can do is to relate the momentum or the energy along this certain U1 direction before and after. So if we do it to the along the now direction, and this P and P bar are just the left moving and right moving energy. And then here is the dictionary. In the string theory set, using TsT, we can just very simply show that the energy along these two U1s are related in such a way. 0 means the energy before the deformation, and lambda means after the deformation. And the dictionary is as follows. The TTbar deformation parameter mu is related to the TsT parameter lambda in such a way, and this momentum are just the energies in the CFT, and they match. And so you may wonder, the string theory contains both long strings and short strings. Long strings necessarily have a non-zero winding, and that's how the spectrum match. But we still have short strings, and short strings can also have zero winding. And what goes on with this? So I would say this is if we do the same trick, we'll find that it is impossible to fix the SL2 representations because there's no winding around. So in order to satisfy both Virasoro constraints, the only way is to map states in different SL2 representations. And for short strings, this J is just minus H, where H is the spacetime conformal weight. If you do so, you'll find that this deformed conformal weight will have a weird square root structure. And what's the role for these short strings in the single-drift TTbar deformation? We don't know. It's very interesting to find it out. Yeah. Okay. So then there are lots of things we can do. As I mentioned, we can generate lots of black hole solutions, and we can work out the gravitational charges and these energies. The energy, left moving energy, right moving energy, and the black hole entropy, they satisfy the same relation as the single-drift TTbar entropy formula. And there's also interesting mapping with the parameters. So there's when lambda is less than 0, in the dictionary that corresponds to mu less than 0, or recall that there's problems with high energy. And in the bulk, what happens? When lambda is 0, there will be CTC. If the bulk has a circle, a spatial circle before the deformation, then after the TsT will get a CTC. And meanwhile, at the same location, there's also curvature singularity. So you cannot really go all the way to the boundary. And if we are in the safe region where lambda is between 0 and a half, then we'll have this black hole solutions. And of course, there is a critical value. This lambda equals a half. And how do we detect that? So recall in the field theory set, it comes from the ground state. And in the bulk, what corresponds to the ground state? In AdS CFT is global AdS. And after this TsT, we can still find a solution that mimics global AdS. It is a smooth solution with no horizon, no singularity in the interior, and it can be found for arbitrary lambda. But if lambda is greater than a half, what happens is that the dilaton will become complex. If we are in the safe region, the ground state is smooth and real, but otherwise there will be problems. here is the diagram, so showing what happens to the curvature when lambda is negative. There is a singularity in between. Okay, so we can also, okay, consider the, sorry. Yeah, there's, sorry, what was my question? Sorry, which way am I going? Oh dear, sorry. Oh, which way is back? This is back?
I think that's back. You're going 35. You're going backwards.
Oh, yeah, okay. So there is also some discussion on the patterning function. So I'll skip that. And then correlation functions and symmetries. So there's a beautiful calculation on the string worksheet for these two-point functions back in the 2017. They found that there is some structure of the two-point function in momentum space. It's this shift of the conformal weight is actually what I mentioned before, is the shift of the short string sector. There are also some calculation in the TTbar set, the ordinary double twist TTbar set. There are perturbative calculations, also non-perturbative results by Cardi, and it shows a structure. This momentum space two-point function has. It looks like there's a shift in the conformal weight, which is like by it's polynomial in lambda. So you may wonder why the two things are not the same. The answer is they are not the same because what we expect for this single twist TTbar duality is that the long string sector with non-trivial winding, non-zero winding can be mapped to the TTbar result. In particular, if we are doing calculations with ordinary TTbar, then in the bulk, we should consider W equal to 1. And this is essential. And with that, we can just have a quick look at how we recover this shift of conformal weight using TsT techniques. So what happens again is that we have two spectral flows. The ordinary one that introduce this with this ordinary W and this TsT introduce the spectral flow. If we combine these together, and when we want to talk about correlation functions, we have to consider it on the plane. And in this case, the TsT direction and this the winding W direction, they are different. And then you'll see that the shift in this conformal weight is precisely this polynomial structure. And in momentum space, this two-point function can be written very simply. So before the deformation, if we normalize the two-point function as the in the Fourier basis in such a way, then after that you get this deformed two-point function with h shifted by this polynomial. And this agrees perfectly with the calculation of Aharoni and friends. They use this JT gravity technique to calculate the TTbar correlation function, and in the high energy limit, they agree precisely. Okay, then finally, let me mention the symmetries. And there are previous work by Monica and friends on the field series set and also about the TTbar-deformed symmetry, and also supergravity perturbation analysis. And the result is that in certain non-local coordinate, you can find two Versors. They are non-local, but they are commuting. And a question for us is that can we find asymptotic symmetries in string theory? And in order to do so, we need to understand how do we, in general, characterize asymptotic symmetry on the string worksheet. And our proposal is very simple. So recall what are exact symmetries. Exact symmetries in spacetime are global symmetries on the worksheet, and the generators are another occurrence. And for asymptotic symmetries, it's similar. You just consider this asymptotic symmetries. But what do we mean? Suppose the target spacetime has a radial direction by asymptotic symmetries on the string worksheet. I mean that it preserves the worksheet equation motion and stress tensor up to a certain fall-offs of this radial direction. And once you have this notion of asymptotic symmetry on the worksheet, you can go ahead and find the asymptotic Killing vectors that preserve this symmetry and write down the approximate charges. You can do it in both Lagrangian formalism and Hamiltonian formalism. And just to show you as an exercise, we did it for three-dimensional flat space and found the BMS generators. And we can also do it to this TsT transformed theory. And here is the final result. If we write everything back into our physical variables, here is the symmetry. It's very nonlinear, but it agrees with previous results. Okay, so here is a summary, and I leave the screen here with some open questions. With that, thank all of you.